This isn't going to be a warm-up question right now because we already walked through this, right? We talked through each of those experiments and we decided that we wanted to compare what experiments? Having labels can help, right? With that. What experiments did we want to compare? When we compare 1 and 2, why did we pick 1 and 2 as a comparison?
Because there's only one thing being changed.
The hydroxide constant stayed constant, which means hydroxide concentration stayed constant. So if we looked at our general form for our rate expression, rate equals K, we're just calling it CH3, which I know is wrong. Don't give me a hard time. Too much of a hard time. We'll call it green and red. Okay. We don't know the order with respect to those reagents because we just have the overall equation. We would need a mechanism to describe that. So we create a reaction, or we run a sequence of reactions, and we would just test what happens when we modify the concentration. And since hydroxide doesn't change, okay, we can effectively eliminate that from our rate expression. So now the only thing affecting the rate would be the concentration of our CH3 compound. The CH3 compound, what did we do to the concentration?
Doubled it.
We doubled it. So we can then go back and look at the rate. What happened to the rate?
Doubled.
It doubled. So what does that mean X has to be?
2.
Okay, so I heard a 2. So let's drop the 2 in and see what happens. If I double the concentration of the CH3, what should happen to my rate? It should quadruple. Okay, that's what that order means, is squaring it. Did the rate quadruple? No, it doubled. So what did the order have to be? 1. Whoops. There are mathematic ways to set that up so that you can see what that solve is. I have no problems going through and doing that, unfortunately not within class time. Okay, so if you want to see that, you can talk to me after class or office hours and I can walk through all of that. Okay, so that gives us our order with respect to the CH3. What did we do to figure out the order with respect to the hydroxide? We compared experiments 1 and 3. Why do we compare experiments 1 and 3? Okay. When we look at experiments 1 and 3, the hydroxide concentration changes, but the CH3 does not, which means my rate is now solely dependent on the concentration of my hydroxide. Okay, so I don't have to worry about the CH3 anymore, so I have a modified rate law. Okay, what happened to the concentration of hydroxide from 1 to 3? It doubled. What happened to the rate? It stayed the same, which means does changing the concentration of hydroxide in my red rate expression change my rate? No. So what must the order be?
0.
That Y must be equal to 0. Okay? Those two pieces of information we can combine to then set us up with our overall rate law, which will be our rate equals K times our CH3 thing to the first power. No hydroxide. I can completely drop that from the expression because anything held to the 0 power is 1. Make sense? So the experimental evidence gives us our rate expression. What we saw previously, in fact on Tuesday, we looked at a mechanism and said, what did that mean our rate law was? Now what we're doing is looking at experimental evidence and saying what our rate law is. Kind of make sense? Cool. So with that rate law, we could then go through and look at mechanisms. So there are 2 ways in which this overall reaction can happen. If we look at mechanism 1, it looks very similar to the overall reaction. That's because it effectively is. We're saying it's a 1-step overall reaction. In mechanism 2, it's breaking down into 2 steps. It's saying I'm going to break the bond to the bromine first, then I'm going to make the bond. So it's 2 individual steps. Okay? Write out the rate expression for each of those mechanisms. Talk to your table to try and sort through what you got. one of your classmates brought up an interesting question, so I want to kind of point on this, because I think it's a good observation to make. When we looked at the individual mechanisms in their examples for those orders, okay, for instance, I think it was blue, I could be wrong on that, but we took 2 blue balls and we smashed them together and we made one product. Okay? And so the argument that you're making, which I think is a great one, is that if we look at this first mechanism, I'm taking 2 things and I smash them together and I make 2 things. Does that match the blue pattern? No, something weird is going on here. Okay? This can be what happens when we try to oversimplify and make kind of pictogram systems. When we're looking at this reaction, what's the only part that we care about with our blue balls? What's the only part that we care about? So, I'm sorry. The left side. Well, if I only care about the left side, should I care that I only get 1 product in the picture versus 2 products in the reaction? Interesting. That's irrelevant. Okay? So really what this diagram was initially saying is I'm taking 2 things, smashing them together, and I make a product. What is the composition of that product? I don't care. It's irrelevant. Does that help a little bit?
Yeah.
Cool. Work again. So let's go ahead and talk through this. What is the rate law? Or in fact, the question is saying, does it match? Okay, we don't even need to know, does it match? What we want to know is, what are the rate laws for each of those individual mechanisms? Once we know what the rate laws for those mechanisms are, we can then answer the question, does it match? Okay. So to start, we should be able to identify what a rate law is. Okay, and I think a lot of people might be kind of losing track into the big questions and not answering the simpler questions that you need to get to. To decide if the rate laws are the same, you have to know what the rate laws are. Okay? So we've got the rate law for the black one written out. We'll talk through that one in a second. Let's take a look at the mechanism 2. Where should we start our rate law? I would argue step 1 is a great idea, but no. Make it easier. You're making it too hard. What should I start writing down? Rate equals K. Yes. We know that has to be true. That's going to be there. Okay? Now I have to put in the bracket stuff. Well, what bracket stuff am I going to put in? Now that I'm talking about what bracket things, that's talking about concentrations. That's now talking about the slow step for the reaction. So now I can say which of those reaction steps is the most relevant to the overall rate for this reaction. Well, step 1 or step 2? Step 1, because it's slow. So what would be the rate expression for step 1? Well, rate equals K times the concentration of the reactants. Okay. Does it show up twice? Is it CH3 plus CH3? No. So what does that mean the order is? As first order. So that becomes our expression. Kind of, sort of?
So is it fine if you're still able to keep track of your reactants to write it in, I guess, a short notation, like what you've done here, or are you going to be expected to write the whole?
So that's a good expression. We are crunched on time. I'm trying to crank through as much material as possible. I'm going to take as many shortcuts as I bleeding can.
I guess I'm just asking. Like,
should you?
Yeah. Should I? Like, if I.
That's a good question. Should you take shortcuts? No. Okay. Which is an unfortunate statement, but yeah, you should not be taking shortcuts. Or I should be talking faster. Those are our 2 options. I need to remove shortcuts, but talk faster to make up that time difference. I would argue I should talk slower and then take shortcuts or a little bit of liberties with our drawings. Does that make sense?
Yeah. This might be off topic a little bit, but if you look at the one-step mechanism, does the rate have anything to do with the separation of a reactant? Because you can see that the CH33 CBr separates and breaks apart, but the OH doesn't break apart.
True.
Does it have anything to do with it being a 0?
So for the first step, is it? Or mechanism 1?
I mean, the OH is 0 and the CH3PR is the first power. So.
Okay. So for mechanism 2,
yeah.
Is the hydroxide involved in the slow step?
No.
No. So I don't care necessarily about, oh, the CH3 is breaking apart and the hydroxide is not necessarily doing anything in that step, because the hydroxide isn't doing anything, period. So talking about the bond formation with the hydroxide is irrelevant. But if I looked at mechanism 1, is irrelevant. Yeah, it is relevant, because I have to make the bond between the oxygen and the carbon at the exact same instant as the bond between the carbon and the bromine is broken. Okay? So depending on the mechanism, it's going to change your response to that, or my response to your question. Does that make sense? Now that we have rate laws for those individual mechanisms, what we could do is go back and look at the rate law produced from the experimental evidence. And what was the rate law from the experimental evidence? Which one did it match? Mechanism 2. So what does that mean about this particular reaction? That experimental evidence that I have collected tells me that this particular chemical reaction happens in 2 steps. That's what it tells me.
Because neither of the steps match the initial mechanism.
False. Step 1 of mechanism 2 directly matches. Okay? And you might be able, you just wrote CH3. Okay, so let's stop taking shortcuts. What was the CH3 compound? It was CH3, 3-CBr. Does the rate law for mechanism 2 match the rate law for the overall reaction? Okay? And it can be hard. There's lots of information out there, so I don't care about mechanism 1 right now. I see rate and I see rate. I see equals and equals. I see K and K. I see concentration CH3, 3-CBr. CH3, CBr. Do they match? Yes. So the rate law for the overall reaction matches mechanism 2. How did I get the rate law nice and beautifully typed in black? Where did that come from? Say again? That was the previous slide. That rate law in black was based solely on, I can't go back. That rate law in black is 100% from over here. That's it. Where did my rate law in red come from? It says lowercase, we'll stick with the lowercase. Where did I come up with the rate law that says this? Where's my rate law in red coming from?
It's coming from step 1, which is the slow reactant.
That is coming from that mechanism. And within that mechanism, I know only step 1 is relevant because the first step was slow. Okay? So in black, experimental data. Red, I took a guess at how the reaction could happen. Okay? And came to this mechanism. Maybe one of your questions is, where did this mechanism come from? Is that the question? Okay. Which is an awesome question. I love that question. That's okay. That's not this class. What you're told is this is a mechanism. Does this mechanism match the data? That's all you have to do. You don't have to know why the mechanism comes into existence. That why is an awesome question. I would love to talk with you about it. Different time. Okay? So what we're trying to do is reconcile 2 pieces of information. Okay? Or 2 ways to get to a piece of information. The piece of information we want is the rate law. We can figure it out by looking at a mechanism and saying the slowest step is going to dictate the rate of my reaction. Or I can look at it from experimental data. Okay? And ultimately, those 2 sources had better come to the exact same conclusion. Because what does it mean if they come to different conclusions? It's the wrong mechanism. There's a mistake in my hypotheses that build out that system. So I must go back to both the experiment and to my mechanism discussion and say, how else could they have happened? You are not responsible for coming up with the mechanism. What you're responsible for is, here's a mechanism. What does it mean? Kind of, sort of? Sir?
Will there ever be multiple slow steps in a mechanism?
No. So you're going to deal with one slow step. The question becomes is, where is that slow step in your mechanism? Is it first or is it second, third, fourth? Okay? That question is one I can't answer yet necessarily because I haven't had enough time to review all of the slides and see what questions Dr. Schnoblin wants to ask. At this point, I'm going to say your slow step is the first step and that's it. Can you have it later? Yes. Absolutely think makes things more complicated. In reference to making it more complicated, go back to Tuesday's lecture video and look at the ozone discussion. Because in the ozone discussion, I pointed out why it becomes more complicated. Okay. The rate law is useful. So we have experimental evidence that this rate law exists. Okay, so yay, good deal. I know this. Okay. But it's also only useful if I can apply that rate law to a new situation. Okay? So if I go back and now change the concentration of CH3CBr, or tert-butyl bromide, can I predict the rate? Okay? So we got some head shakes. Yes, yep, absolutely I can. So let's test you on that. Here's this system. The initial rate for this reaction was 0.3214. That's way too many sig figs. Let's make life a little bit better. 321. What was the concentration? It's going to become a little bit harder to predict, right? Okay. We might be able to make some guesses and approximations off of this. Okay. But if we switch out of easy patterns, really what we're talking about is that if I'm going to solve that expression, my rate equals K, I want to know rate if I know this number. Let's give you a different one, 4.16. What's question mark? What was this? Is this you just doing your own thing, or are you saying no, that this you can't do this? Okay, that's fine. What is question mark? Yeah, what's the number? Why are you saying that? What does shoulder shrug mean? We haven't defined what K is. To get a formal rate expression, we would have to define what K was so that we could extrapolate this out to any individual experiment without having to reference back to different experiment systems. So how do we figure out what K is? Say again? You've got a bunch of experiments, okay? Do we know the rate? Experiment 1, yeah, 0.011. Do you know the concentration of CH3, blah, 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 blah? Yeah, we know that. Plug that in. So we've got two numbers we could plug in. How do we solve for K? Some people are like, oh, it's just algebra. Okay, ideally we would see that, but maybe not. So K for experiment 1 is going to be 0.011 divided by, where'd it go? 0.05, yeah? Cool, we now know K. What are the units on K? What were the units on the 0.011? What were the units on 0.011? Molar per second. capital M per second. What are the units on 0.05? Molar. What happens?
Inverse seconds.
The molars cancel. Your units on K will be
Inverse seconds.
inverse seconds. Okay? That's why that slash in there is nasty. You got to watch out for that slash. Generally speaking, I would prefer to write it as capital M over S to help emphasize that fractional thing. We could then run through the calculation. Does somebody give me a number? Somebody.
Or no, sorry, that's basically
0.22. Cool. That was K for the first experiment. We'll call it K1, right? Because we said 1, 2, 3. How do we figure out the K for experiment 2? How do we figure out the K for experiment 2? It's the same process, right? You know. K2 equals 0.022 capital M over S divided by 0.0. Someone needs a better attention span, I think. That's me, by the way. And I would get 0.22 per second, right? That sounds kind of familiar, doesn't it? Yeah, it sounds kind of like the value we got for K1. What was K? A constant, which means for every experiment, what should K be? The exact same numerical value. Once you've solved it once, you've solved it forever. Hooray! Now you could go back, plug K back into your expression, your rate law, and for any rate, you could determine your concentration that you would need to get that rate. For any concentration, you would be able to determine the rate of the chemical reaction. Make sense? Okay. Which takes us. I didn't update this. Dang it. Okay, it's not active. It's Alex, due Sunday. I think it's officially number 2. The quiz isn't mentioned. Oh, the quiz is mentioned up there. It's not next Wednesday. Dates are really problematic for me right now. It's not next Wednesday. It's the following Wednesday. Okay? Where's the information for that?
We don't have class Wednesdays.
Thursday.
Okay.
It's not next Thursday. It's the following Thursday. I already said dates are bad for me. Where's the information for that? And don't tell me the slide, because the slide's clearly wrong. It's in the syllabus. It was freaking me out. I had no idea when it was, because someone asked. And I was like, oh yeah, the syllabus. Check the syllabus. The syllabus has that calendar in there. Okay. I wouldn't be surprised if that appears under Mike's information, and I pull it out of the syllabus, so I don't have to dig into the syllabus to find it. Okay, so be aware of that for your quiz. Okay. Stuff for the Unit 1 quiz. The practice thing should be coming up soon. You get one sheet of paper, so it's not, and I'll check with her, it's not formally open notes, just one sheet of paper. So bring your note, your one sheet, your calculator, pencil, paper. You get a periodic table and all that. Yeah? Cool. Here we go. New one, right? That's a new equation. Put it together. What do we want to look at? So first and foremost, cool picture of what this stuff is used for. I don't really care. That's a bit callous. I do care, but it's blocking my writing space. If I'm going to look at my rate law, K, my rate for the overall reaction will be rate equals K times the concentration of my reagents, ClO2, that's a Cl, not a U. Stop giving me a hard time. And then times concentration of OH. Awesome. But I've not defined what the orders are yet. So that would be an X and a Y. Because we're feeling all Christmassy, we'll say green and red, right? So it's Christmas spirit. Yay. Okay. What experiments do you want to look at? The first and second. Okay, let's take a look at the first and the second. Okay. And if all we're going to do is look at the first and second, that's it. We don't care about reaction 3. what things change. So maybe we should try it this way. She suggested the first and the second, so a different group. Why should we look at the first and the second?
We can see the ClO2 go up by 3 and the rate goes up by 3, so that's pretty useful information, I guess.
I would backtrack out of that.
Hydroxide remains constant.
I'm picking those two because one of my variables, so if I'm looking at this system over here, one of my variables stays constant. The hydroxide concentration does not change. Okay? Which means if I'm going to look at that experiment, or those two experiments, my rate law is going to be equal to K times the concentration of ClO2 to the X power. I can ignore the hydroxide because it's not changing. So I can completely drop it because it's not going to have an effect on the rate. Okay? Now that I know that, what happened to the ClO2 concentration? It tripled. So if that goes up 3 times, what happened to my rate? It went up also 3 times. So what must X be for this expression to be true? It has to be 1. Okay? 3 to the first power is 3. And you might be, well, what about the K? We don't need to stress about the K, and we can make this a little bit crazier. And by a little bit, I would actually argue a hell of a lot crazier. Rate 1, concentration 1, and we could say rate 2 equals K, ClO2, concentration 2, still to the X power. Okay, so all we did is say what the rate law was for the second experiment. Okay? Since we know the K's are constant, what can we do? We can say K is equal to rate 1 over ClO2 to the X power. And we know that is also equal to rate 2 over ClO2 to the X power. And if you're looking at that going like, this looks really ugly, I don't really like this, this is making me uncomfortable, then stop doing it and just guess at your numbers. Okay? But ultimately what we're doing is we're comparing rate 1 to rate 2, equaling ClO2 1 to ClO2 2. I know the change there was 3. I know the change here was 3. So 3 equals 3 to the X power. What must X be? 1. Okay? That's the kind of mathematics that supports what we're going through and doing. Or, ignore almost all of that. Get rid of that little 1, because we don't want to deal with that 1. We look at it and say, what happened to the rate? Well, it went up by 3 times. Okay? And what we're estimating in our heads is saying this goes up 3 times. If the ClO2 goes up by 3 times, what does X have to be? Note, what we've done is cheated all the mathematics and just jumped straight to the end of it. Okay? But the mathematics actually support why we're able to make those conclusions. Okay? And if you don't like dealing, because you can actually solve that, you can actually do math, natural logs, and all that fun stuff to get to what the X value is. Or you just say, well, is it 1? Yeah, done. Wrong? Okay, is it 2? Yeah, done. Okay? And you can do simple substitutions. Because what are the possible values for X? It's a hint. There are 3 possible values for X. 0, 1, and 2. Plug and chug.
Not dealing with anything else.
And then you don't have to stress about any of the mathematics. When do you have to worry about the mathematics? If you are explicitly asked to show the mathematics behind it. My understanding is you won't be explicitly asked to do that. Kind of, sort of? Okay. One of our tendencies is it goes up by 3, so X must be 3. That's why this question is here. That's not what happens. What we have to do is see how each of those 2 things go up relative to each other. That's why it's an equality. Make sense? So cool. This tells us that X is, stupid stuff behind it, 1. Okay? Is that our answer now? No. We haven't checked, at least as a class together, what is the Y value? So I would go back to my data set and say, what's going on within this data set? Now, what 2 experiments do I want to look at?
2 and 3.
Okay. Why did you pick experiments 2 and 3? Somebody else.
The polarity for ClO2 stays the same.
ClO2 doesn't change, which means when we're looking at our rate, it effectively boils down to rate equals K times concentration of the hydroxide to the Y power. What happens to the concentration of hydroxide when I compare 2 to 3? It triples. What happens to the rate? It triples. So our hand wavy approximation, our rate triples and our concentration triples. What must Y be? 1. We can now change out our Y value to be 1. Now what do we do? Connect them. Tie them all together. Those things in green and red were approximated rate laws. They were only approximated because we removed one of the concentrations as a factor in our rate. We deleted its value. Again, the mathematical setup of running the rates equal to each other could show you how that works. Okay? So we now have to combine them. So we would say our rate equals K, concentration of our ClO2 to what power?
1
1 times the concentration of
OH
OH to what power?
1.
1. There's our rate law.
Now, why is rate still K instead of being 3? If that's which is what I thought was just defined to conclude that.
Did we say K at all anywhere in any of these? No, we have not defined K at all. What we looked at was how the rate went up and how the concentration went up. We ignored K. Why could we ignore K? It was a constant. Okay? What was the exact quantity for K? I don't know. I didn't solve for it. But as long as I know it's constant, for the sake of approximations, I can make it whatever I want. And that making it whatever I want allows me to make this simple comparison so that I can drop in the order. Okay? And I see some people being like, I don't like that. That's cool. Here's the long answer. Because here's what you are asking for in all its gory detail. Rate equals 1 times K times the concentration of ClO2 to the X power times OH minus to the X power. This would be for the concentration 1 and 1. So for an individual experiment, experiment 1. Okay? I also know the rate for experiment 2 is going to be equal to the constant, or the rate constant K times the concentration of ClO2 to the X power for the second experiment times hydroxide to the Y power for the second experiment. I know the rate constant is equal to rate 1 over ClO2 X hydroxide minus to the X. Yeah? I know a green one. K equals rate 2 over ClO2 2 to the X OH minus to the Y 2. Yeah? Now what can I do? Set them equal, because K's are equal. So I can erase that. Well, I don't even have to erase that K. I can just say these are equal to each other. Okay? And now I'm definitely out of space, but what I'm going to do is also do a slight rearrangement. I'm going to bring the rates. I'm going to group the rates together, which means I want rate 2 over here. And I want all of these concentrations for 1 over there. And I'm going to get rate 1 over rate 2 equals concentration of ClO2, 1 to the X hydroxide, 1 to the Y, over, I already switched to different colors, ClO2, 2 to the X, OH minus to the Y, squared, not squared, experiment 2. This is why this notation gets painful. What are the meaning of those numbers? Okay, and what did we do for experiment 1 and 2? Why do we pick experiment 1 and 2? You've got the table, I don't. OH is constant, which means whatever this value is, and whatever this value is held to orders, is going to do what? Cancel. What happened for the concentration of ClO2, 1 to 2? What was the value for 1? I genuinely don't know. The value for 2. Rate 1. What was the value? 0.041. Over. Rate 2.
0.124.
Okay. This value is now 1 over 3. Ah! This value is now 1 over 3 to the X and to the X, right? Can we do some fancy math there?
Logarithms.
1 to the third, 1 over 3 to the X power. We can distribute that. Why has that become valuable? Okay, so deep breath. I got our race. There's no space. Let's erase the top. So we're cycling up. I get 1 over 3 equals 1 over 3 to the X power. What must X be? 1. That's where it comes from. That's the mathematics that we just hand-waved our way through. But you requested the mathematics, there it is. Okay? Most people don't like this. Why not? Your handwriting sucks, Mike. Oh, probably dislike it for other reasons. It's not that bad. Okay? You're looking at very complex variable systems that you're grouping together as a single unit. Okay? Students tend to struggle with that a lot until you have practice enough with it that you can say, that is a single thing. That is a single thing. And you can start to cancel those terms out. Most people don't like to solve the equation. They want to plug in the numbers first. The numbers can become very misleading unless we understand the mathematics behind it. Here's the mathematics behind it. Your choice. You do the longhand mathematics or you do the abbreviation that we just walked through. That is literally your only two options. That's it. Okay? With that, I apologize. Okay. What do we move to? What does that tell us about the mechanism of the reaction? Tells us it's second order. Right. Single step gets a little potentially wonky because if we go through and do this, we need 2 ClO2s. And if we looked at our rate law, how many ClO2s do we have? We just had 1. Right? But our rate law is saying ClO2 must collide with OH minus. That's going to be a slow step. It's going to produce something. That something is probably going to collide with another ClO2 or an OH minus to then make our products. But that extra step is fast. I don't care. The only thing I care about is that initial slow step. That is one possible way to explain it.
I just have one question, because it also said please find the rate constant. So I was trying to figure it out on my own, but I keep getting different constant numbers for each experiment.
That's pretty sketch.
Doing it correctly.
Okay, so if we're going to figure out the rate constant, what do we have to do? K should equal ClO2 to the first, OH minus to the first, over I knew I should have written it out properly the first time. And when you do that substitution in for each of those individual experiments, you're getting different values.
They're roughly the same, but slightly different. I'm like getting.
Give me some numbers.
For like experiment 3, I got 4.4, and then for experiment 1, I had 4.1.
1, you got 4.1.
And then in between is like 4.1333.
4.1333. So, go for it.
The initial rate isn't exactly 3 times as much.
So some of that is going to be variation within experimental data. So that becomes a real fun conundrum within this. We're making the assumption that everything was perfect. Okay? We just said 3 times, and you said it was not exactly 3 times. So when we go through to run this, we're going to get a couple different variables for what the rate constant is, but they're all pretty darn close. How can we get a single value? Average those experiments to bring in a rate constant that's now kind of in lockstep. What that should do is minimize any of those random fluctuations that were not perfect transitions. Does that make sense? Whoa, goody. Summarize by filling in the table. Okay, so this is summarizing everything. Everything that's been addressed. So this is not for an individual experiment. This is everything we talked about. If it's a zero-order reaction, what would you expect your rate law to be? What's the first thing you should write in that first column? Thank you. Rate equals K. Next one. Rate equals K. Next one. Rate equals K. What's the next thing we need to write in? Concentration. Concentration of what? Reactant. What do you want to use as your symbol for reactant? Okay. Some people are saying A, perfectly acceptable. If it's a zero-order reaction, what needs to be the superscript? 0. Can I write that for the rate law for the zero-order reaction? Yeah, that's perfectly acceptable. Is there a better way to write it? Rate equals K. Because A to the 0, doesn't matter what A is going to be 1. So I could just write rate equals K. What happens for the first order?
First power,
Awesome. Second order.
second power.
Cool. What are your rate constant units? That one gets a little bit more dodgy. So what I'll have you do is now start to work through the rest of those, and we'll come back in a second. Sorry, I got to interrupt. Good question was brought up. For that first order, okay, where we're writing A to the first power, do you need to write the 1? No, you don't. You absolutely do not. Why would I suggest writing the 1? Because you're going to call attention to it being the first order. So if you're answering a question, that might help you recognize that is first order because you're seeing the number. If you don't need that extra hint, that's fine. Don't worry about it. Drop the 1 off. Okay, we're definitely going to hit a weak spot here in a second, which we'll see for me. What are our rate constant units? Well, to track the units, track the things that you already know. What are the units on rate? Our molarity over seconds. So for that very first box, for our zero order, what must the rate constant units be? It's an equality, which means the units on one side must equal the units on the other side.
M times 1 over.
What does the rate constant have to be? Molarity over seconds. That's the only way that equality works. So the units for a zero-order reaction for rate constant is m over s, molarity over seconds. How about for a first-order reaction?
Inverse seconds.
Inverse seconds. fancy way of saying it, or 1 over s. What happens for a second order?
1 over s squared.
1 over s squared. What are the units on A?
Molarities.
Molarity. So if we run this question, you're going to get
Molarities squared.
over seconds squared. Is that the unit for your rates?
Gotcha.
Okay. So you'll cancel one of the units from your concentration of A, leaving the other one behind because we need it. And the rate constant is going to still need that inverse seconds so that we get the seconds in the denominator.
So writing that as like, for the first order, would it be acceptable to just do s to the -1? So it's seeing it's also written like that wrong.
So deciding how you want to write that, the notation, is ultimately up to you if you want to do s to -1 or 1 over s.
And then the second one would be just ms to the -1 if you were writing it like that.
I don't know that I've seen ms to the -1. You might see this
Yeah.
because you have to make sure that -1 distributes. Typically what I think they'll do is capital M -1, S -1. They'll show that all the way through. So why change the notation? Y'all are too young. You don't know why. Old people know why. Because we had to transfer this knowledge from one part of a country to another country, which means we had to send it through a piece of paper. How did the information get onto the piece of paper? It was typed. And if we're using a typewriter or a computer, doing a fraction 1 over s was really hard to do, even like 50 years ago. So we do s -1, because it means the same thing. That's the only reason that notation exists. I would argue the fractional notation is much better, because it allows you to see your numerator denominators and deal with units and cancellations and all of that, whereas the s -1 requires a little bit of mental gymnastics. Okay, here's my weak spot. What are the graphs supposed to look like? Okay, I see what you're saying. So flat, okay, as you change the concentration of A, what should happen to your rate? That's supposed to be a flat line. The rate shouldn't change. Okay? What happens if we move to the first order? As we increase the concentration of A, your rate should go up. If it's second order, what happens? Yeah, thank you. Okay? And that, I would push you to pay attention more in mathematics than I did.
So we had a little disagreement. So for the second one, the second order, not the second one, but the last one.
Okay.
Well, I was saying I thought it was linear, but with double the slope of the second one because the rate, as the rate doubles, the other one should double, right? So
But it's
like,
careful. When you double the concentration of A, what happens to your rate?
does it quadruple?
It quadruples because of the squaring. So it's not just doubling. We good? So when A doubles, oh yeah, look at that. It answers the question. So in the last one, when A doubles, what happens to your rate?
Stays the same.
For the last one, sorry. Because we just talked about that. Quadruples. For the first one, when the rate, I don't know why I wrote rate. Times 1. Does that work? Does that make sense? It stays the same. It's not going to change. Okay? For the next one, it's going to double. Kind of getting it? Yes?
So when would you use the graph like that? Like
I don't see that graph up here, so I have no idea what you're talking about. I know, it's like 2 slides later. Give me a sec. Okay, so our rate constant units, okay, we just talked through that. Hopefully we got that. Feel a little more confident about it. You're effectively just solving each of those rate expressions, but you're ignoring the numbers and just using the units that you know to be true. Okay? Which then gets us to our graph options. The first one makes a lot of sense. Hey, look at that. I almost drew that perfect. I didn't draw that perfect. Okay. You told me what to do. Okay, we've got our 0 order, our first order, our second order, and then what the hell is that? Is that third order? No, it's not third order, it's logarithm. Anybody know what he's talking about? Okay. Something else weird is going on here. What's going on weird here? Biochemistry. This is talking about a catalyst. All right. So a catalyst is involved, which means the catalyst starts binding. So as we increase the concentration, the catalyst speeds the reaction along. So the catalyst can grab the reactant, make product, make product, make product. Eventually, you add so much reactant that can the catalyst grab it anymore? No, the ratio of catalyst to starting material has shifted, and you have an excess of reactant. The catalyst can't speed the reaction up anymore, which means what happens to your rate? It flattens out. Right? That's something that you would typically see in, say, a biochemistry class. She has a lot of biochemistry experience, so she's pulling that out, planting a seed now for anybody that has to take a biochemistry class where you would then talk about rates. Okay? And you'd see plots like this for things that are catalyzed. Does that help answer your question, now that we're looking at the picture? Okay. What is the rate constant? Okay. The rate constant effectively factors in all those things that we've already kind of talked about. Remember, did we do the pen? We did the pen. I don't have a pen. I have a pen in my hand, right? Right? And I'm trying to put the cap on. That's just stupid, just smashing my hands together. Okay? Right? Chemical reaction. I have my reactants to make a product. Ta-da, there's product. Okay? But chemistry is just these things are bouncing around. Okay? Sometimes they'll collide. Does that mean we had a product? Do I have it? I don't. Okay? What else do I need? I need the proper orientation. And when we look at our rate law just says concentration. It says nothing about orientation. Well, is the orientation something that we can see or control? Not really. Okay? Catalyst brings in a separate question. Ignore that for the moment. Okay? But is it something that would be constant? So said another way, as I try to cap this pen, is there any other orientation that gets me to the product of the capped pen? I mean, I can turn this around, and let's not do that, but if I smash that, okay, that's not going to cap. There's only one orientation, which means for an individual reaction, it is constant. Well, what was K? K was the constant. K is that thing that envelops all this extra piece of information that becomes a little bit harder for us to quantify. Okay? What else does K incorporate? Is my pen capped?
Orientation.
Oh, no, it wasn't. Change your words, but yes. The energy necessary to clear the activation barrier, to switch from reactant to product. So our rate constant factors some of that stuff into it. Right? Again, that's constant at a given temperature and other conditions. So this is why changing temperature can change our rate constant. Right? Because if we look at our energy diagram, it's still going to be about the same, whatever, close enough. But if we're looking at our ball sitting at the bottom, we're not going to get very many particles over. But if I give that ball more energy, what does it do? It's going to move back and forth, which means particles that have a higher energy have what activation barrier to clear? A slightly smaller one, so I can increase the speed of the reaction. Okay? That's a transitional activation energy, so we can't really quantify that. What we can quantify is the total energy. So if we change the temperature, our rate constant is also going to change. Which means if we're going to start studying rate constants, we have to lock in our temperature so that we're seeing a consistent reaction. Okay? That takes us back to this plot. Okay? As we increase the temperature, what's going to happen to this plot? Okay, well, let's walk through some meanings behind it. What is this point? For those people at home, we'll draw it. What does that point mean? What does that red dot mean? All right, what is this axis? The y-axis representing? The molecules. So if I have a point that's really low on the y-axis, what am I saying? Very small amount of molecules, yes. Okay? It's also to the extreme left on our kinetic energy plot, which means low energy. Okay? So if we look at an individual sample at any given temperature, okay, or a group of people at any given temperature, what we'll find is they all have different kinetic energy. Okay? They will all move differently, but we will always have that 0 point. Why? What are our particles doing?
Moving.
And colliding. And if there happens to match a perfect system within the billions of possible collisions, that you have equal mass head-on collision, what happens to the kinetic energy of those particles? It cancels. They have 0 energy. Okay? Very swiftly, another particle is going to come through and knock them, and they'll start moving again. Okay? So you will always have this 0 point. Okay? The max point at the other end is going to be very, very, very low. Okay? So what we get is effectively a distribution. And if I increase the energy, I can't change the number of particles. So the area underneath the curve must be the same, because it's the same number of particles. But what happens to the curve? It squishes. And at a higher energy, I now have those particles at a higher spot. Why is that relevant? Well, activation energy is a marker, a random marker, not random, but for an individual reaction, it's a constant marker along our axis. Boom, that's my activation energy for this reaction. So if I look at the blue temperature, very few particles clear that activation energy. But if I increase the temperature, all of those particles now also clear it. So it's going to change my outlook on the experiment. Kind of make sense? Much better drawn equal areas and all that fun stuff. So increasing the temperature in order to increase the rate of the reaction, we do it every day. Pizzas, cooking. That's the whole point of that, is to speed the reaction along, because otherwise we just end up with a gooey mess. Okay, or a not gooey mess. Okay, so how would we go through and deal this? Somebody very smart went through and started to quantify all these little pieces and come up with ways of what things can we monitor, and when we can monitor those things, how can we relate that into a different system? And what we get is this system called the Arrhenius equation. The Arrhenius equation allows us to relate some interesting factors. Okay? What's the first factor that looks familiar to you? I'll give you a hint.
Okay.
You didn't even look at my hint. But K, yes. What was K? Our rate constant. Okay? Which is interesting because that's what we said. The rate constant factors in all these extra little pieces that we don't know how to deal with them. Okay? And we said, what other things? What other things stand out at you that we potentially already talked about? EA. This is our activation energy. So this is interesting. If I know enough information, say about the rate constant and maybe some of these other terms, I can actually determine the activation energy for a reaction. That's pretty wicked. What else do I recognize? You recognize A? Where did we talk about A? Ooh, fair play. A, we talked about our rate law, right? Rate equals K. Trust me, that's what that says. Our rate law is where we said A. What was A in that? What did that mean? It was a random variable that we picked to represent our reactants. Okay? And we knew they were reactants because we used conveniently these brackets. That rhymes better in my head. And what do those brackets reference? Concentration, molarity. Do you see the brackets? No, this isn't concentration. This A is something else. What is the A for? Totally making this up, by the way. Arrhenius. It's an Arrhenius constant. So we introduce a new constant. that constant is going to factor in some of those pieces that are intangible, like the orientation of our reactions. We still can't quantify that well. Okay? What other things come into this that you recognize? Okay? Slow your roll just a half step. R, okay. What do you see for R? Say again?
Rate?
Rate, not a bad idea, but no. Because when we talk about rate, we wrote out R-A-T-E. We didn't write capital R and then just said it was equal. We actually wrote out the word rate. What'd you say?
0.0821.
What the heck is that?
Oh,
Equals that.
R, also known as the gas constant. And the gas constant you just threw at me was liters times atmospheres per moles times Kelvin. Okay, which is going to become important. And T is our temperature. What was, yes. What was EA? What units? Joules, kilojoules, a measurement of energy, right? Anybody see a problem with our gas constant showing up in here? Yeah, okay, you said yeah. What's your problem with it?
There needs to be the kilojoules.
What the hell's going on with the units? Well, it turns out the gas constant can be converted from what you're used to using, liters, atmospheres per moles Kelvin, to torrs, okay, to a half dozen other things. And one of those other things it can be converted to? Joules per mole Kelvin. You just gave me a number. 8.314, and that was joules per mole Kelvin?
Yes.
Okay. This is going to be something to pay attention to. That's joules. Joules are small. Activation energy is typically large, so our activation energy is usually in kilojoules. Are we going to have to worry about unit conversions? Yeah. Be careful. Pay attention to that when dealing with these conversions. And so what we're now going to do is look at the Arrhenius expression and all the different mathematical things that we can manipulate within that. Unfortunately, we are not doing, well, unfortunately, we're not doing that today because we are done.